What's up, Advanced Chem? Good morning. Want to do a quick check of what we learned yesterday. So I want you to take a second, pause this before you go on. No cheating. And draw what each of the following would look like when dumped into this beaker of water, according to our flow chart that you guys wrote down yesterday. So you have hexane, which is C8. Oh, I'm sorry. That's actually a mistake. That's octane, C8H18. And sodium carbonate. And it doesn't really matter that that's actually octane because octane and hexane would do exactly the same thing. So I want you to pause and try it and then see how what you have compares to what I have. Okay, so if I were to do hexane, or what it should be, which is octane, C8H18. This is actually a liquid at room temperature. And it goes, well, octane is completely nonpolar. So is it ionic? No. Is it polar? No. And that's because the bonds are all between carbon and hydrogen, which have a small difference in electronegativity, so it's not polar. So this octane is going to have no change whatsoever. It is not going to dissolve, so no sphere of hydration. And it is not going to dissociate because it's not ionic. So that one is no change at all. Sodium carbonate, on the other hand, if I were to write its formula, it would be Na2CO3, sodium being a +1 ion, and carbonate being a -2. It is a solid at room temperature, but more importantly, is it ionic? Yes, it is ionic. And then using my solubility chart for my next question, is it soluble? Yes, it is soluble. So when sodium carbonate goes into water, we would expect that this would both dissolve and dissociate into ions. So I'm going to draw all my ions dissociating. So I would have two sodiums, and they would both be in a sphere of hydration. And then the carbonate ion, being polyatomic, would stay together, but it would also dissociate from the two sodium ions. And so all three of those would be aqueous. We would write this as 2 Na+1 aqueous, and just the one CO3 -2 aqueous, and this solution would then have an I value of 3 for the two sodium ions and one carbonate ion that we would get for every Na2CO3 molecular formula unit that is added to water. So I hope that went okay. Out of those two solutions, would one or both or neither conduct electricity? B is electrolytic, and that is because it has free-flowing ions in it. So a solution that can conduct electricity is called electrolytic. And sodium carbonate, because of the fact that it has those ions that are just floating around now, it would conduct electricity. Okay, so let's quickly talk about three different types of equations. We have molecular equations, and this is all meant to help us write what's called a net ionic equation. And so we start with our molecular equations. So in a molecular equation, all species are written shows all species as full formulas, so a formula equation. For example, if I were to take just a simple double replacement, so I'm coming up with this off the top of my head. If I were to take potassium iodide would be Ki. And add that to lead nitrate. Ooh, I think I gave you this one in your practice problem, so I think I don't want to do this one. Okay, I changed my mind. I want to do, so we've got sodium carbonate decomposing into sodium oxide plus carbon dioxide. So we've got 2 ionic compounds, boom, boom, and 1 covalent nonpolar compound. And this is just the formula written out the way that we've always written out formulas and equations. And it's even balanced. Woohoo! So molecular equations are just business as usual. Full formulas, regardless of the type of compound you're dealing with. Next, we have complete ionic equations. And in a complete ionic equation, it's going to show all ions that exist in the solution. Okay, so for example, if I were to write the molecular formula, ammonium chloride plus silver nitrate, that's a simple double replacement. On the product side, I would get ammonium nitrate plus silver chloride. That's the that's the molecular equation. Now, if I wanted to write the complete ionic equation, I would assume that I take this reaction and I put it into water, and I would show all the ions that exist in the solution as being ions. So what I'm going to do is take each one of these at a time, and I'm going to imagine, using my flowchart, what would happen if that particular compound was added to water. So first I have ammonium chloride, which is ionic, and if I look at my solubility chart, it's soluble. So therefore, it is going to both dissolve and dissociate, and I'm going to write it that way. So dissolving and dissociating means dissociating into ions NH4 plus 1 aqueous and Cl minus 1 aqueous. Moving on to my silver nitrate. Silver nitrate is both ionic and soluble according to my solubility chart, which means it is going to both dissolve and dissociate. Oh, whoops. I don't have you guys here to correct my mistakes. I just have crazy kids running around upstairs being noisy. There we go. Okay, so those are my reactants. Now, if I go down and do my products, I'm running out of room, so I'm going to go down instead of left to right. My products, I've got ammonium nitrate, this guy right here, ionic, and checking the solubility chart, soluble. So if I added that to water, I would get NH4 plus 1 aqueous and NO3 minus 1 aqueous. And then finally, over here on the far right, hanging out right here, is silver chloride, which is ionic, but insoluble according to my solubility chart. So that is going to be unchanged when it hits water. So it is just going to remain AgCl, and it's an ionic compound, so it would stay as a solid. And I want to point out something really important right now, and that is you have an ammonium ion right here, NH4 plus 1 in the aqueous form, that is both present as a reactant, and it is in exactly the same form, meaning it has the same formula, same charge, and it's in the same state, aqueous, on both sides. Because it is the same formula, same charge, it exists in exactly the same way on both sides, what this means is that NH4 plus 1 is really not changing or doing anything of interest from start to finish in this reaction. We call that a spectator ion, meaning it doesn't really participate in this reaction. It's just spectating. It's just existing. It's there at the beginning and it's there at the end, but it is not actually a part of the chemical change. There's another one in here, and that is the nitrate ion. So NO3 minus 1, and it's aqueous. NO3 minus 1, and it's aqueous. Now it turns out in our next type of equation that we're going to talk about, we're going to eliminate those spectator ions so they don't do anything. So in the next type of reaction, we're just going to take this NH4 and we're going to get rid of it since it's not really part of the chemical change or the chemical reaction. Same thing for the NO3. We're going to get rid of it completely and we're going to rewrite it with just the things that remain. Now this is getting really messy, but if you look at what I have here, what's left and not crossed off is Cl minus 1, Ag plus 1, both aqueous. These spectator ions at the bottom, and then you've got AgCl, which is solid. So let's go on to the next slide and rewrite that. So what's going to happen is in a net ionic, so net meaning overall as opposed to complete, we're not going to show all of the ions. We're going to eliminate any spectator ions. And remember that means exist in the same form on both sides. And so rewriting our previous equation, that leaves us with Ag plus 1 aqueous and Cl minus 1 aqueous, and that is showing the formation of silver chloride, the solid, which is a solid, so it is a precipitate in that double replacement. So basically it's showing just the formation of the precipitate, which is the only chemical change that is happening. So I think we're going to stop there for now. Today I'm going to have you try some practice problems on the topics from yesterday and today, and then we will go over it all together on Monday. Thanks for your patience while I've been gone in this crazy homecoming week, and I hope you have a wonderful, fun, restful weekend, and I'll see you on the flip side.